I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on drawing system schemas and free body diagrams. Isaac Newton was arguably the greatest physical genius ever. He published his 3 laws of motion, helping Galileo and Johannes Kepler with their observations. He invented calculus, and he published his principles in 1687 in Mathematical Principles of Natural Philosophy. So we're going to look at Newton's laws from our mallet ball activity, drawing system schema and free body diagram. So what is a force? Simply put, a force is a push or a pull, which is what we did with the bowling ball with the rubber mallet. A force caused the bowling ball to accelerate in 3 ways. By speeding up. First off, when you hit the ball with the rubber mallet, it's sped up in the direction you hit it. We also caused it to slow down by hitting it in the opposite direction. And then we also caused it to change direction. That's when we were navigating through the circular path. We are hitting it towards the center of that circular path by changing direction. So Newton's first law of motion is also known as the law of inertia. Inertia is a word that is used interchangeably by physicists with the word mass. So the word mass and inertia, the more inertia something has, the more mass it has. The harder it is to change something's velocity, the more mass or inertia an object has. So Newton's first law of motion states that an object in motion is going to stay in motion at a constant velocity. That means not changing direction or speed, and it's going to stay at rest until acted upon by an outside force. So either in motion or at rest. When we have an unbalanced force, that would be the rubber mallet hitting the bowling ball, causing it to change speed, direction, which would cause the velocity change. This is the reason for the horizontal component of velocity to be constant for a projectile during its flight, because there are no unbalanced forces in the x direction on a horizontal projectile. So we're going to draw force diagram, free body diagrams. At some point, we're going to need force diagrams. At other points, we're going to need free body diagrams. So force diagram is a vector representation of all forces acting on an object from the origin of the force on the object. Whereas a free body diagram is similar, but it takes that object and shrinks it to a single point. So let's start with a system schema. So a system schema is a collection of objects that have symbols drawn between those objects to represent interactions or forces. And we draw a dashed shape around the object we're going to draw a force diagram or a free body diagram for. So let's look at this physics book sitting on a table. We've got the table, the earth, in the book, and we're going to draw our dashed shape around the book. So now we're going to only draw the interactions that act on the book. So we know that the earth interacts with the book and the table interacts with the book. Why is this important? Well, that tells us that when we draw our force diagram or free body diagram, we have 2 interactions. So if the physics textbook lies motionless, the gravitational force pulls down, and the table is pushing up on the book. There's no acceleration, there's no change in velocity, so those 2 forces are balanced. So we have this textbook that is being pulled at a constant speed. The key here is a constant speed. That's going to give us a hint for a force that we need later on. So we draw our system schema. We've got the book, we've got the dashed shape around the book, we've got the earth, the table, and the student. So we know that the earth supplies the force of gravity. The table provides an upward force on the physics textbook, and the student applies a force to the right. Now, because there's a force to the right, that means there has to be something balancing it out to the left. And that force is the force of friction. The frictional force acts in the opposite direction of motion to balance this out so that the book can have a constant speed. If it didn't have friction, it would not have a constant speed. Now, that diagram got a little complicated, so we're going to talk about drawing free body diagrams instead of drawing force diagrams. Force diagrams will be needed later on, but a free body diagram, here are the steps to drawing your free body diagram. First, we draw the system schema that we just talked about to represent the situation. We label each arrow with a force, and we'll go through a list of forces in just a minute. Each arrow is labeled with a force in a symbol. Then you're going to draw an XY coordinate system, and the x-axis is drawn horizontal or parallel to the surface. That is important. The x-axis is always drawn parallel to the surface that the object is on. Then we shrink our object to a single dot, and we place that at the center or the origin of our XY coordinate plane. And then we draw vectors that all start on the dot and point away. All vectors have to start on the dot. So here's a list of some common forces that we would label. So the force of gravity we can label with Fg, or as we learned in our lab, mg. The normal force, which by definition, the normal force is the perpendicular force between the surface and the object. That was the table pushing up on the textbook in the previous two examples. So we'll label that with Fn. The frictional force, which we had in the previous problem, which is F with the subscript of F. A tension force would be a rope or a cord or a string pulling something. We'll call that Ft. If you just a generic push or pull force, we can call that Fp. A buoyant force, which would be a force supplied by the water, would be Fb. We also have a drag force, which would be something that's rolling, or drag provided by wind resistance if a ball is falling through the air, which is Fd. A magnetic force, which is Fm, produced by two magnets or a magnet. Electrostatic force would be charged objects, like a balloon on a wall would be an electrostatic force. Now, for the most part in Physics 1, we're going to focus on mostly these forces here. The other ones are more Physics 2. So let's look at drawing a free body diagram, following the steps from previously. So we first draw our system schema. We have the floor interacting with the box and the earth interacting with the box. We want to label those forces on our system schema. So the floor on the box is the normal force, and the earth is the gravitational force. So we have Fn and Fg. Then what we're going to do is we know our box has two interactions. So we draw our x and y coordinate system, the x-axis parallel to the surface. We shrink our box to a single dot in the center. And we know there's only two interactions. So we draw the normal force pointing up, and we label it with the normal force, and the gravitational force pointing down, and we label that force with Fg. Now we know that the forces have to be balanced because there's no acceleration. The box is just stationary. So we can see that we have the normal force, gravity, two interactions on our system schema. Now let's think about the bowling balls that rolled through the no-touch zone. So the bowling balls that rolled through the no-touch zone, we know that it had a constant speed. So here's our system schema: earth, mallet, floor, ball. The earth and the floor interact with the ball. Remember, it's in the no-touch zone, so the mallet does not come in contact with the ball, so there is no interaction between the mallet and the ball. The earth supplies gravity, the floor the normal force. We draw our x and y axis, and then we shrink to a single point, and we have those same two forces, the normal force and gravity. Now, this looks very similar, in fact, identical to the free body diagram from the box, but this one's moving and the other one's not. The key is they both have a constant velocity. There's no acceleration. If there's no acceleration, then the free body diagrams, the forces all have to be balanced. So in this case, the normal force and gravitational force are balanced as well. So let's look at a little more complicated situation. So we're going to draw a free body diagram for this stationary box on an inclined ramp. So we have the box, the earth, and the ramp. Now the interactions are between the ramp and the box, that's the normal force, and the earth in the box, that's the gravitational force. Now we want to draw our free body diagram. Remember, the x-axis is drawn parallel to the surface, and then the y-axis perpendicular to that, with our box being the dot in the center. Gravity is always going to point towards the center of the earth, which in this case is down. In most cases is down. Sometimes if you're in outer space, it would point to the center of the earth depending on where this earth is. Then we have the normal force perpendicular to the surface, which means the normal force will always be drawn on the y-axis since it's always drawn perpendicular to the surface. Now, in this case, in our inclined ramp lab, this would have caused the car to accelerate, but the box is stationary. That's a hint that tells us that there has to be another force keeping it from moving, and that force, again, is the frictional force. So another interaction between the ramp and the box. Friction is going to oppose motion. That box will want to slide down that ramp, down in the x direction, which means friction opposes that motion by pulling back up the ramp. So we draw our free body diagram with three interactions to cause this box to be stationary as it sits on the ramp. Since we have an angle, we're going to label that angle, and we'll talk a little bit later on in a later video why that angle is in between the y-axis and the force of gravity. Now let's look at a box being pulled at a constant speed. So it's being pulled with a rope at an angle. So we draw our system schema. Constant velocity tells us that there has to be friction since it's pulled. So we have two interactions from the ramp, normal and friction force, gravitational force from the earth, and a tension force from the rope. So the constant velocity, again, is the reason for the frictional force. We know there has to be a frictional force because of that constant velocity. So now we draw our x-axis parallel to the surface. In this case is horizontal. The y-axis is perpendicular to that. We shrink our box to a single dot in the center, and then we proceed to draw our vectors to represent the forces. We have gravitational force down, tension force up and to the right at an angle, the normal force up along the y-axis, and frictional force opposing the motion of sliding across that table. So we have our free body diagram for our box being pulled at a constant speed as it slides across the table. That's how you draw system schema and free body diagram. That's just our first step in what we're going to do in the next video. I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.